So welcome to this Learning Machine seminar today. Today I am going to talk about machine learning for particle-based simulations. My name is Olof, for those of you who don't know me. I work at RISE. I'm a researcher working on machine learning for many different applications. I have sort of dipped my toes a little bit into this physical simulation world together with some colleagues. For example, Olle is here today. I hope we'll have some nice discussions also with some people who actually know some physics. So please interrupt me if you have questions. I'll just go right into it. Also, since we have people with a little different background here today, I thought I'd start with some of the groundwork, bring us up to some of the basics here. So what is physics actually? It's the study of matter, motion, behavior, also energy and force. This is the first paragraph of the Wikipedia article, and also these nice illustrations. So this is apparently physics. I think some physicists may also say that today it's going to be about classical mechanics. Well, what is modeling then? Everybody uses the word modeling. Not the least people within machine learning. We model things all the time. I think also people in physics model things all the time. Most of the time, we do refer to things that are almost the same thing. So a model is something that we have to understand, to define, to quantify, visualize, or simulate something, a part or feature of the world. In this definition, this is also from Wikipedia, they say that when you model things, you reference it to existing and usually commonly accepted knowledge. And this may be a place where us machine learners and other people diverge a little bit, because people within machine learning generally don't know so much. So they don't have this knowledge that we should connect it to. Instead, we'd like to infer things from data. And well, we definitely, when there are knowledge, we try to connect things. And sometimes that succeeds. Right? Interjections, intermissions, objections. Now let's go on. So what is machine learning then? I would say many participants here are of course familiar with machine learning. Within machine learning, we create learning algorithms that train models that we use to predict something. Now, the predictions we want to do about the world and the models we like to train using some part of the world that we call the training data. So we'd like them to learn stuff from viewing, from observing stuff. One of the popular classes of machine learning algorithms or models is what's here referred to as neural networks, and those are loosely inspired by by how your neural network in your brains work. Thus, the engineering tip from XKCD. Some of the nice properties with machine learning is that we don't have to explicitly tell our computer programs what to do. Instead, we tell it how to learn stuff from the data. This can have sometimes efficiency improvements, and it can sometimes also make systems more robust. All right, so those were the initial basics. Now let's talk about machine learning for physics. Whatever machine learning is and whatever physics is. So in 2015, Ladicki et al. Presented this paper using regression forests which is another kind of machine learning model. It's not a neural network, where they trained this model using data from a simulator called PBF solver, position-based fluids. They trained this model to approximate Navier-Stokes equations, which has requirements on momentum, mass, and energy. And so they trained it to predict acceleration of particles in this system. And they did this in 3 dimensions. So some of the outputs you can see here to the right. They did not make too bold claims. They did claim that their simulations looks plausible, but they're not perfect. They're not exactly as a simulation from a real solver. So that was just one early attempt. What we'll focus more on today is a solution that builds on graph networks. Graph networks is neural networks that work on structured data structured using arbitrary graphs. A graph is a set of vertices and edges. Edges connect vertices, and this can encode a number of different properties of data. In this setting, we will have vertex features, which is a vector associated with a vertex. We'll have edge features. We call them E here, and that's a vector associated with every edge, with each edge, sorry. And we also have global features, which we call boldface U here. So graph network takes a graph in and gives a graph out, where you do some processing and using this first phase, which is called the message passing phase, vectors will be communicating and processed throughout the graph, which will give vertices knowledge about neighbors and about neighborhoods of graphs. So not just direct neighbors, but larger neighborhoods than that. The second phase of the graph network usage is the readout phase, where you more or less take the final step of this message passing phase, and you process it through another module, and you read out the results. You train these using end-to-end training, since the whole thing is a neural network, and you can train it to predict different attributes about this graph, or about nodes in this graph, or about edges in this graph. Questions? I'll go a bit more into what graph networks are. So as I mentioned, this is a graph-to-graph function approximator. So we learn a function that takes a graph as input and gives a graph as output. In the nomenclature here, we have the input graph G with vertex set V, and the output vertex set V prime. So we have the same structure between input and output, but we have processed things. So this function have learned a transformation from the input graph to the output graph. Right. So the picture from the previous slide is on the bottom left here, and that's the main structure of the graph network. Here we have a number of different modules, and we have some names for those. So we have the phi v, which transforms the state of a vertex. So the state vector of a vertex called v is transformed using this phi v in the middle. That's the node block. It takes as input the current state of the edges connected to this vertex. It takes as input the current state of V, and it takes the current state of the global graph, which is called U here. Now, to compute this, obviously we need to have the edge block on top here, which is computed by the phi e, and the phi e takes the current state vector for the edge, the current state vector of both vertices that are connected by this edge, and the global features U. We also have this global block that transforms the global state to the next global state. It takes as input representations, the states from each edge and each vertex in the graph. And this is the message passing that's being done in a graph network. So these five functions, these are learnable functions, and in all the instantiations of this framework that we'll see today, these are fairly small multi-layer perceptrons. So a couple up to 4 layers and some hundreds of dimensions per layer. Together, of course, the whole thing becomes a rather deep or large neural network, since the output from one such module is fed as input to the next one, and the whole thing is trained end to end. Right. So we compose these GN blocks, and that's what we call the message passing. So here we say that we work with M messages, and that is M repetitions of the applications of this GN block. So what we call the GN core here is the M number of GN blocks, which transforms the graph from G0 to GN. G0 is just some reasonable initialization, which we will mention soon, what's included in this. Yes, so G0 is here computed by the GN enc, and we take the decoder output in the end and give us the output. So graph neural networks, there are a number of different flavors of this. Perhaps some of you have seen graph convolutional networks. Here it's listed as number 5 from Kip et al. In 2017. But there are several different variants, and number 6 here from Gilmer et al. Called neural message passing is actually a paper that builds together many of these approaches and gives a common nomenclature to compare these, and they are actually very similar, and the convolution part is more or less equivalent to the message passing idea. Right. I included here a link to a YouTube video with a presentation of this Gilmer paper, the neural message passing paper, because if you're interested, that's a good way of getting sort of this umbrella view of what was the state of the art in 2017. Okay, back to the graph networks. One instantiation of them is called interaction network, IN. It was presented by Battaglia et al. In 2016. He's now at Google DeepMind. And in this paper, they model small physical systems, such as this 3-body system, where we have a complete connected graph. We model this system as a complete connected graph, and the edges encode relations such as gravity. and here the vertices have the color of the body in the visualization to the left. So the left is a visualization, the right is the corresponding graph, and the network works on this graph. So first we apply the edge functions, the edge function phi e, as in the previous slides, where we take the current state of the edge, we take the current state of the two vertices that are connected by this edge, and we compute this as the next state for this edge. We do the same thing for all edges here, and then we do the computation for the vertex states. That's called node function here. So node and vertex, I use them interchangeably. I'm sorry if that confuses you. Node, vertex, same thing. So then we take the phi b here, and we take the edge state, and we take the vertex state and the global state, and we update things here. And then we do this a number of times for each vertex, and we train this to predict something. In the end, we also have a decoder step that predicts potential energy of the system, and apparently here we also have a comparison. In many other papers here, it's really difficult to compare one system from another. I don't really know why. Perhaps it's because these are a bit computationally intensive. But here we have compared multi-layer perceptron, that's a simple architecture, with the interaction network, and we get a lot lower mean squared error on the positions of the particles. So this is another slide from the same paper with some more information. So we have 3 different classes of simulations here. So as you see, we have 6 different columns in the illustrations, and there are 2 columns for each kind of simulation. First the true one, and then the model one. So the true one is the kind of simulations that was used for training, but these are held out for validation. For the first problem, which is this multi-body system that we just saw, the simulations look fairly similar. In the bouncing balls, I don't think you can actually see that the balls bounce in any way similar. Please correct me if I'm wrong here, but at least the authors claim that, well, that should also be plausible trajectories for bouncing balls in such an environment. And I guess they're right. It's not entirely random, at least. In the rightmost 2 columns, we have a string of objects that are connected by springs. So those are the blue and lighter things. And this string falls down with gravity towards this ball, and then I guess it hangs around this ball. I guess the simulations are fairly similar to the true ground truth here. So what's nice about this solution? Oh, there's one more thing I should mention. The inputs are these objects, and for the leftmost problem, those are the bodies. For the middle problem, we have the balls and the walls. So the walls are also objects or particles that interact with the balls, but they are sort of dead. They cannot be updated in any way. And then we have the point masses that represent the string element in the rightmost one.
Could I ask a question?
Yes.
So when you looked at this, how is the position typically represented? Is it Cartesian coordinates, or One could think of
So,
other, so
yeah,
spherical coordinates, or for example, distances between
yes.
particles.
So I actually don't remember from this paper, but I know from the follow-up paper that we will come to in a minute that the positions are part of this state vector. The initial state vector, they encode actual knowledge of the initial state of the system, and there you have absolute coordinates for the vertices. For the edges and for the edge update functions, at least in the follow-up work, they mask this information so that the edges don't know the absolute position of the objects. And the edges include information about the relative position, but not the absolute position. Was that an answer to your question?
Yes, very good. So in particular, the edges encoding the relative distance, I think, is in a very interesting, let's say, invariant representation of positions, especially
Yes.
for the kind of system.
Yes.
Thank you.
Yes, good. And this in this case, the model is trained to output the velocity in 2 dimensions, so one x-y coordinate. It's trained with single steps. That you're given one input state, and you do the message passing, and then you predict the next step. And on evaluation, this is rolled out into a longer trajectory. And so they say that they generalize to systems that have another number of particles, and I guess that's the main strength here. That's the main generalizability evaluation. As I previously mentioned, the phi's here are fairly small multi-layer perceptrons. So that is straightforward neural networks, which are trained end-to-end in this graph network setup. Right. Okay. So a follow-up paper for this, which was actually accepted to NeurIPS in 2017. So the previous paper was presented at NeurIPS 2016, and this is NeurIPS 2017. They do almost the same thing, but they add a convolutional encoder, in the sense that they are simulating the same problems. The multi-body system that has the gravity, that's the first 2 rows here, I think, or the second row, sorry. First there's the spring problem, and then there's gravity problem. And then you have the magnetic billiards, and then you have the billiards, which I think correspond to the second problem in the previous paper. And then you have some sort of drift, which I guess it doesn't have the same kind of collisions. But the main difference is not the tasks. The main difference is that the input is not a representation of the locations of stuff. The input is here. They call it a video. I guess it is a video, but the background image here is just a randomly sampled picture from Cypher 10. And they claim that this is to confuse the model. I guess it adds some difficulty for ComNet, but the convolutional encoder, it sort of has to fulfill the task that was just inputting locations before. So this can infer the locations and then do the simulations, and it seems to work. Right, so fast forward a bit. Now in 2020, this paper was presented, or it's not presented yet, I guess it's on archive, where they make larger simulations of more particles, and they do this in 3 dimensions, and it seems to look fairly cool. They still have this data that's generated from simulators. They do work on problems that have different kinds of particles. So for example, we have liquids, we have, they call it goop. I think it's the slimy thing in the middle here. They have sand and they have solid objects. I think they may have a couple more in the experiments as well. So here they claim to generalize a bit more. They generalize to new initial conditions, more particles, and many time steps. And it looks fairly successful in the evaluations. Although there are things to complain about in the evaluations. So the input particle states is similar to the interaction network paper. Many of these two papers share many of the authors, by the way. So the state, the vertex state has position, and that is the absolute position. They have 5 previous velocities from 5 previous time steps, and that's part of this input particle, the input state of the particle. They also have some static features, such as whether it's water, whether it's sand, whether it's goop, rigid, boundary, particle, and so on. The edges, misspelled here, they are added to the graph when 2 particles are within a connectivity radius, which is a hyperparameter that they specify or search for. The prediction here is not velocity, but it's acceleration of the particles. And when they have predicted the acceleration, they use the Euler integration to actually do the simulation. And that is just taking a step in the direction of the velocity. For the training data, they use the simulators Flex for the domain that's called box path. Here, domain is, I suppose, the physicist sense of the word domain, in that each of these settings is sort of one domain. That is one environment for the particles. I would assume that it specifies the boundaries, edges, and whether there are some specific hurdles or objects in this simulation which are not the actual particles. So the first domain is called box path, and it uses a position-based dynamics method, PBD. It's called Flex. In the water 3D, you'll see these domains in a minute. Water 3D, they use an SPH-based strict volume preservation method called Splish Splash. For some other domains, there are more domains in this evaluation. They use the Taichi NPM engine. So, as I said, they claim that they generalize towards larger systems. They train on up to a couple of thousand of particles, and they test on up to 85,000 particles. They train on one time step only, as I said before. So you have one time step as input, and then you predict the next time step. And that's the only thing you do during training. They test it on up to 5,000 time steps. And that is just dreaming away for the model. So when you predict the next time step, you use that as the initial state for the next time step, for the next prediction.
Sorry to interrupt here, Olof,
yes.
But you said something about that they took 5 previous time steps into account. Was that some kind of initialization from the beginning? It's not something that is made in each time step. 5 previous velocities.
Oh, yeah. So these 5 previous velocities, when I read this, I actually interpret it as for each application of this learned function, which is only one time step prediction. So when you apply this function, you get the prediction for one time step, and I interpret this as you are storing the 5 previous velocities? Yes.
Mm.
Would you consider this cheating?
No, it might be a good way of doing it. Seems
Yeah.
like it could be beneficial to have some history on the velocities. Yeah.
Yes, I would say that the input state is fairly small in the number of features. It's not a high dimensional vector here.
No.
And yes, from 5 previous time steps they store this.
Mm.
Okay, so these are some demonstrations from the experiments. I actually don't know how many time steps they run these for. So we have 8 different domains here, and on the top row we have the initial starting condition, and then we have the prediction after the rollout. That is, we make this up to thousands of time steps, and the final row here is the simulator's data, which is considered to be the ground truth here. Colors are different kinds of perhaps it's not. Perhaps all are liquid here. I have to look that up. But things sort of fall down in this domain, and they fall on the solid obstacles, which are here in black, which were specified in the domain, and they get splashed out in the bottom. And I guess these predictions look fairly similar to the ground truth.
When I read the paper, I interpreted that it was the blue was water, and the brownish was the sand, and that purple stuff was the perhaps non-Newtonian fluid that they simulated.
Yes, it also looks that way, I guess. So the water makes splashes,
Yeah.
and the goop thing, perhaps it's looks a bit more
Slimy, as you said.
less viscous.
Yeah. Mm.
Yeah. Okay. So I thought we'd look at some videos, but these were opened in a new window. Perhaps I should try to share that window instead. Share my desktop instead. Do you see this this video
Yes.
window now?
Yeah.
Yes.
Good. So we have these simulations that look fairly plausible and also similar to the ground truth, I guess. These are different initializations. So they initialize with water in different places of this box, and then they let it fall down.
And am I correct to understanding that these are essentially extrapolations of the learned model? So you learn a model in very few time steps, and then you run it tens of thousands of time steps, only with the learned dynamics.
Yes, but you, yeah. So you have all the training data is only one time step at a time.
Yes.
But then you have many of such examples. So I actually don't know how to close that window. I'm such a boomer. my colleagues would say. So I thought we'd look at some more of these. Particularly one thing that they brag about is the box path. There's a still frame from the paper where they demonstrate that alternative, a baseline where they fail to retain the box's shape. Here, the model has correctly learned that the yellow kind of particles, they don't break apart, more or less. So there comes blue particles and they float around the yellow ones, but the yellow ones, they can move, but they stay together with their yellow bodies. I guess these are perhaps similar to the ones we saw before. And so this one is also something where they demonstrate the generalizability, because they add more particles as they go along, and this wasn't seen during training. There's this here we see the training domain. So in the training domain we only have the finite number of particles, but at test time we add more particles. So it looks like there's a pipe of filling this box with more water. So as you can see, many of these are two-dimensional, but there are also three-dimensional ones. And
one question on this initial, you train on one time step, they train on one time step. If you just let the water fall, it will take some while before it hits the boundaries or the floor. How does it know how to handle the floor then?
I would assume that you pick or you do pick random samples from complete trajectories that were made by the simulator. So when you create the training data, you create these whole training trajectories, and you give the model one frame or one state, one randomly sampled state as input, and you train it to predict the next state, or the acceleration in the next stage, more specifically.
I think you had one of those movies on that page that shows the training domain. I think you might, if you stop the video when the training domain is shown, it might be easier to refer to that one. There you had it, a smaller training domain up in the right part of the image on the, I think, what was it, water vortex or
water vortex?
Some of the other.
This one, generalization experiment. Yeah, so this one we've already seen, right?
I think the training domain flashed by in the later part of one of the videos, and one could see that the training domain kind of captured the different physical scenarios that the water. Yeah, there you see the training domain.
Yeah.
So it was
all right. That makes sense.
Smaller.
They randomly sample from it.
Yeah, and even if we're not training with the whole rollout at once, we will be sampling frames where particles are at the edges. So we will be sampling examples when particles are bouncing off edges and stuff like that.
In the case of edges, the boundary here, is that represented as particles, or is that some other kind of representation, or a fixed, so to say, edge representation?
I think it is a kind of particle. So it is part of the graph, but it is a fairly special part of the graph because it's not really updated. So you never change the position of the edges, for example.
Like the ramps in the bottom example here. Yeah.
Yes, those are also they are particles, but they're not updated. So that's sort of hard coded.
Yeah,
it feels like the particles on the edges in that case would need to be able to represent the common boundary conditions you use in classical CFD simulations, like slip boundary conditions or similar.
Yes.
Yeah, similar kinds of boundary conditions.
Okay, I'm sure you're right.
But that would be something that's learned from the training data, because there are, if I understand correctly, there's no prior on the physics.
No, there's not really a prior on the physics here. No.
But isn't the
So
training? Isn't
I
the
guess
training
there is a prior in the sense that boundaries cannot move and so on.
But isn't the training domain compared to the simulation results from the other softwares you mentioned in the beginning? You listed the 2 or 3 simulation softwares like the Splash and
yes.
like
what
that
do you mean
would.
about this?
Sorry,
I thought perhaps I misunderstood, but I thought that those served as some kind of reference.
They are references, but you do some special handling of these boundary particles.
Mm.
In the sense that you don't model them, you don't allow the network to update them. You don't compute updates for them, but you do allow the moving particles to interact with them.
Yeah.
So you get edges between a moving particle that comes close to the edge and so on. So regards to your question about this one-step training, you do a similar thing when you train recurrent neural networks for language, to generate language. So either there are sort of 2 different ideas there. Either you do the teacher forcing, in that case you do the next step prediction. In the recurrent network, you predict the next word based on the assumption that you did predict the correct word in the last word. So the previous word was assumed to be correctly sampled, and then you sample the next one. And that has some limitations, and you often do a mixture of both. So you sometimes let the model wander, and sometimes you let it be forced by the teacher. But there is this problem with letting the model wandering, because if you roll out this system for 500 time steps, the state of the learned system may have wandered off from the ground truth system by quite a large bit. And when you have wandered off so much, then the learning signal will become not very reasonable. You will get gradients that want you to move these particles by a lot. So instead, you assume that the previous time step was correct, and then you train it to make the correct next time step. Now, this has some other limitations, such as what happens if we start to actually end up, or we start to get into states where that we didn't see during training. And one of the remedies for this is to add some random noise, and they do that here. They add some random perturbations for the for the locations of the particles in the input. So given a perturbed location, predict the correct next step.
So the output then, is it probabilistic, or is it just a regression? Likely the latter.
I think it's just a prediction, actually.
Yes.
I think it's a 2 or 3 dimensional real valued prediction.
Yes. So just the regular conditional mean.
Yes,
So
exactly.
I have a question.
Yeah.
How long time does each of these simulations take to run? The ground truth simulation and the predicted one?
That's a really good question. And many times these solutions are motivated by a speed up, that it does go faster than the original simulations by the CFD software. And I still assume that this is the case, but they haven't actually explicitly said that in this paper, which rings some alarm bells.
Yes.
And in the previous publications, I mean the original interaction network publication, for example, they had up to, I think, 14 particles in one simulation, 14 particles in 2 dimensions. Here we have 85,000 particles in 3 dimensions. And so these neural networks, there are modules here, are fairly small, and I guess it should scale with the number of edges which would be less than quadratic, I guess. So
it seems like it seems like there are large possibilities to tweak the solver here to make it more or less complicated by changing the interaction radius for the particles and reducing or increasing the number of interaction in that sense, number of edges, if I understood the technology.
Yes. And they look for as a hyperparameter, and I think they optimize that parameter for the best performance. I guess if you lower that parameter, that value, I guess you will have worse quality in your simulations, but faster. Yeah, you will get fewer.
But all of these examples, it seems like the problem is very local. The interaction between particles is very local, right?
Yeah, it is. Yeah.
You have gravity, and then you kind of have the particle bouncing against each other.
Yeah.
But you don't have more complicated, like long-range interactions, as I would. So imagine that we would like to do this for a molecule. Then I guess you would have a lot more, like the electromagnetic forces would also exert. You might have longer range interactions.
So perhaps you would actually go with the complete graph in that case.
Yes, that's a suggestion I've heard.
Mean, you would in such a graph neural network, you would learn what kinds of edges you have, but you will also have smaller graphs, wouldn't you? What yes. Are some large molecules? How large are they?
I mean, large molecules can be very large, like proteins, but often the kind of molecules we are considering are typically quite small, so a couple of 100 atoms at most, and quite well. Then we also typically consider the bond structure, but I'm thinking that.
But then you'll get some tens of thousands of edges if you get a complete graph.
Yes,
and that would probably be feasible, I would assume.
Yes, or yeah, but perhaps you could actually using windowed approach is probably a good idea to make it more general. I don't know, or some kind of graph pooling step, like if you see in PointNet++, where they, which is also kind of close to these ideas of using, let's say, a window. You induce a neighborhood through some kind of radius. But that would be interesting. But that's just from what I see, an observation that all these domains are fairly local interactions.
Yeah.
And then I wonder how it would generalize to, let's say, more and body problems, essentially.
Yeah.
No further comment from me.
I have no answer on that.
No, that's an open question.
Yeah, should go through the last couple of slides here.
Yes.
Okay, so some ablations are in the paper. There are not many comparisons to Baseline's method. They mention this continuous convolution paper which they take up as sort of this failure for other methods for this solid box in water. And so they brag about this box being retained in the water, but CConv, it garbles the box, even though it retains, it does stay together, the green balls, but not as good as the graph network. So the ablations here are looking or more hyperparameter search perhaps, is they use 10 number of messages, and increasing number of messages was always better. So I guess there comes the time constraint. I would have liked them to say how much time this take. So apparently, if you have many more steps in the message passing phase, you get a really good increase in performance from 9 or 10 such steps when you do the rollout. It doesn't show so much when you do the one step as you do during the training, but it really shows when you do the longer rollouts. Shared GMs means that the graph network that you do apply 10 times, that is the 10 messages, you can either share weights for each such application, so that you apply a similar or the same module all the time, or you can train different weights for the 10 different modules, and then it's more or less 10 different neural networks, even if it's trained end to end. But they get a really good improvement in performance for the rollout, when they not share the weights. So they don't. Connectivity radius, well, 0.015, whatever that means. So larger connectivity gives better performance, I guess is the takeaway here. It's a bit surprising that they have chosen the edge conditions here, because we don't know if you increase the radius even more. I guess again it will take much more time, both for training and prediction, but we don't know how much. They should have included the time here as well. The noise, as I mentioned before, the noise is in the input representations for the vectors or the vertices, the input representation vectors for the vertices, and they have a standard deviation of 0.0003, whatever that means. Relative positions, as I mentioned when we talked about the interaction networks. So either you let this transition function that works on the edges, either you let it see the absolute positions of the particles, or you mask it out, and you only give this transition function relative offset. You give it both direction and magnitude of this offset. But apparently relative positions is much better, at least in the rollout. And then you have the comparison between the CConv and the graph network solution, and for all the evaluated domains, the latter is significantly better. And these are mean squared errors for the whole rollout, which means that you're measuring the offset for each particle from the ground truth. So this is another paper from the same group. I just want to briefly mention, I'm sure many of you saw one or two of these papers that worked on this simulation environment. So this paper from ICML 2018 in Stockholm, by the way, they trained using Q-learning this agent to walk around or to balance these bodies in this environment. But what they also did was they used this graph network. The graph network was a part of that Q-learning approach, but they also used this graph network to infer properties about the system, given how it looks. So they can infer stuff like gravity or material properties and so on. What about COMNETs? What about LSTMs? Haven't people done that? Well, sure, they have. I just mentioned a couple of them here. I think it looks like they're managing to do fairly well with this as well. I don't think this deep fluids paper is a great paper. They claim that they train general model, but then they don't make so bold claims as to generalizability and so on. And they do it in 2D and 3D with smoke and goop and liquids. And then there's this LSTM CNN hybrid, which also seemed to do some level of success in the plausibility of the simulations. Right. So this is the reading list. Now you do the homework. Comments, questions?